G'day guys, and welcome to our lesson on light and interference. There was some discussion in the previous lessons about the wave-particle duality of light. When you're discussing light interference, it's best to think of light as simply a wave. And that wave behaves very much like a sound wave, or the way we're going to visualize it, little ripples in a pond. So the basic principle behind wave interference is this. If you have two waves that match up perfectly in phase, there's one wave and here's the other, and this here is the zero line, the resulting wave is extra big. It has a high intensity. And if you have two waves that is in phase, that's constructive. And if you have two waves that line up like this, completely out of phase, and this is the zero line here, the resulting wave will actually be flat. You'll have no intensity, and that is called destructive interference. And this occurs, of course, in ripples in a pond, but it's also observed when it comes to the interference of light waves with each other. So this diagram here that I've drawn up, we have two point sources of light. I've drawn them different colors, but since the wavelength here is the same, we know these should in real life be the same color, but I've drawn one as yellow and one as white. I'll try to refer to them as point source 1 and point source 2, but I may slip up because I'm staring at these colors on the screen. So let's look at how at different points these light waves are interfering with each other. Let's look at this point here. We have the crest of a yellow wave. I've done it already. The crest of point source 1 meeting the crest of point source 2. So we have a constructive interference there. Furthermore, at this point here, we have the trough of point source 1 meeting the trough of point source 2. Therefore, we have an extra large trough in the resulting wave. So when two crests meet here, or two troughs meet here, we have constructive interference. So let's circle quickly all the points where we have two crests meeting. We have here, here, here. I'll circle them. So you may be starting to notice they're all falling on these regular lines. So that's giving you a clue to the later part of the lesson, in which we're going to work out a formula for where these bright lines do appear. And also note, in between all these blue dots, we have two troughs meeting. The trough is halfway between each white line and each yellow line, and that is also known as constructive interference. So the troughs meet and the crests meet along these lines. And the most important one is the central one there, which will give us a central bright band. Now let's discuss destructive interference. So the blue will be our constructive, and our purple can be our destructive. Destructive over here is when the crest of one source meets with the trough of another. Yes, that's the best one. Or the crest of number 2 meets the trough of number 1. And we can see that happening where a white line occurs halfway between two yellow lines. So that happens here, 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 here. That's crest from point source 2 meeting troughs from point source 1. Or the crest from point source 1 meets the trough from point source 2. That's there. Oops, there, there. Along. So we have it happening also regularly between each bright band or bright constructive line. We get these destructive lines. So again, constructive interference occurs in regular lines and destructive interference occurs at regular lines. There's another line there. We can draw the diagram to work out where these types of interference take place. But a better way of doing it is discussing path difference. So I'll show you how that works. So say I take a point here, and I draw a path from point source 2 and a path from point source 1. The path from point source 1 is 1, 2, 3 wavelengths, and the path of point source 2 is 1, 2, 3 wavelengths. So when the waves of light from 1 and 2 arrive here, they'll look like this. They'll be matched up in phase. Furthermore, if I look here at this point, the path from point source 1 is 1, 2 wavelengths, and the path from point source 2 there is 1, 2, 3, 4 wavelengths. So by the time the yellow light arrives here, it'll be, we say, 2 wavelengths out of phase with the light from this white source. I'll see if I can draw a diagram to explain this. So the white light will look like this: 1, 2, 3, 4. And the yellow light will only have travelled 2 wavelengths, so it'll be 1, 2, like that. Even though the light from point source 1, I said the yellow light, excuse me, the light from point source 1 is lagging behind by 2 whole wavelengths, it still fits in nicely there. So we find that as long as the path difference of white there was 4 wavelengths, and the path difference of the yellow was 2 wavelengths, as long as the path difference is equal to, say, 1 wavelength or 2 wavelengths or 3 wavelengths or 4 wavelengths, or we just say n wavelengths, the light is in phase and we get constructive interference or bright bands. Lights of high intensity, a big light wave that is going up and down like that. So that explains this formula up here. Yeah, I hope you can see that. So let's look at an example of destructive interference. Where's a good example? We'll try and go on this line here. We'll pick this point. So this point here is 1, 2, 3, 4 wavelengths from yellow, and 1, 2, 3, 4 and a half wavelengths from white. So PL1 is equal to 4 wavelengths, PL2 is equal to 4.5 wavelengths. The path difference equals 4.5 wavelengths. Take 4 wavelengths, that's a half wavelength. If it's a half wavelength difference, it means yellow looks like this: 1, 2, 3, 4, and white looks like this: 1, 2, 3, 4. So it looks like this over here. It's half a wavelength out of phase, and that's when we get destructive interference. We'll also see this when it becomes 3 on 2 wavelengths out of phase, which is a half plus 1 wavelength, or 5 on 2, or 7 on 2. So that explains this formula here. Basically, if we let n equal any number from 0, any integer from 0 to infinity, we'll get a wave that is constructive if you use this formula and destructive if you use this formula. I always make this mistake. I forget that n could also equal 0. Say here, the path length from point source 2 is the same as the path length from point source 1. Therefore, the path difference equals 0 wavelengths, which is where n equals 0. Okay. Using this idea of path difference and path length, we can predict, if we shone the light on a screen here, where certain bands will appear. So we've already touched on this, but reiterating, if we're getting constructive interference, we're getting a very big light wave, and we're going to get a bright band. So I'll just sketch that in here, bright band there, because constructive interference happens on that line. Constructive interference also happens on this line here, so we get another bright band, and down here, bright band, and you can see we're expecting another constructive interference to happen just up there. So the bands keep going, and down here we can actually sketch this one. And since there's destructive interference happening along these lines, whoops, this band should be over a little. This band here corresponds to this line. Destructive interference happening there and there. We get dark bands here. And then again, there. So if we shine these two point sources onto a screen, we get these alternating bright and dark bands. There are certain parameters to this experiment. For instance, the distance between the slits there, the length between, I said the slits, I'll introduce that now. Okay, so instead of setting up this experiment so that we have two point sources which we've got to try and get perfectly in time, what we do, I want that to go away, is we erect a wall here with two little slits in it there. And we beam light that is coherent and in phase at it, these are light waves here, towards those two slits. And just like in water, when the light reaches this slit, it diffracts out like that. And the same thing occurs over here. And since we're using light of a single wavelength over here that is arriving in phase at these two slits, we expect these two slits to act as point sources which are coherent and in phase. So if we put light towards these two slits, this is called Young's double slit experiment, and then the light passes through those slits and ends up on some kind of screen, we expect that bright and dark pattern of light to appear. And of course, since it's an experiment, we can change things, like the distance there between the two slits, the wavelength of the light, the length of the slits to the screen. Yes, those are the three things we can change. And depending on how we change them, these bands will either move further apart, so they look like this, or they'll move closer together, like that. And we set up a little measurement here. We say, what is delta x to the first bright band? We'll calculate that. Well, we know that all along these lines here, actually along this line, all these points of constructive interference, the path difference was equal to a whole wavelength, one wavelength. So we'll use that bit of information to come up with some kind of formula. I'll scale these down over here. Now we have some room. So we draw a triangle. We'll draw it in yellow. There's one side, there's the other, and there's the hypotenuse. The length of this side is delta x, which is the length on the screen from the first bright band to the second bright band. This side here has length L, and that angle there is theta. So we can say that tan theta equals opposite over adjacent equals delta x on L. Tan theta equals delta x on L. So now we're done with that little triangle. We can draw another. The path to this bright band here of yellow, of point source 1, is shown there, and the path from point source 2 is shown here. And here's the clever bit, here's the very important part to remember. If I drop a line here that sits at right angles to this path here, then this little side length here, just sitting in here, what I'm circling, that is the path difference. That is the extra distance the path from white has to travel compared to the light from point source 1. So this is the path difference. Furthermore, that triangle we set up before, here, we said that was angle theta. This angle in here is also angle theta. And we have theta, the hypotenuse and the opposite. So we can say that sine theta equals opposite over hypotenuse equals path difference on D. And here's the small angle formula when theta is very small, on the order of 1 degree. Tan theta is around about equal to sine theta. And if you look at the graphs of these two trigonometric functions, there's sine theta and there's tan theta. As they approach this point here, they become very, very similar. And tan 0 equals 0 and sine 0 equals 0. That's when they become absolutely similar. But the important thing to remember is the small angle formula allows us to equate these two, and therefore allows us to equate these two. Delta x on L is equal to path difference on D. So delta x is equal to path difference times L on D. And we set up here the path difference was 1 wavelength. So a wavelength L on D. That is the distance you have to travel from the central bright band to get to the second bright band. Now the third bright band here is another delta x beyond that. So we can say the distance to get to the nth bright band, n being the, actually this is the first, this is the second, this is the third. So the distance to get to the, we'll say the nth bright band beyond the central is given by n lambda L on D. So the central bright band, n equals 0. You don't have to go any distance. The second bright band there, n equals 1. You have to go lambda L on D. And the third bright band, which is the second from the center, n equals 2. Let's see how this formula can be applied. We'll do a little example question just to finish off this lesson. So we have this formula here. And I'll ask if lambda equals 700 nanometers. That's red light. L equals 2 meters, the distance from the slit to the screen. And the distance between the slits here equals 0.1 millimeters. What is delta x to the third bright band? Bright band. So we'll say this is the first, this is the second, this is the third. N equals 0, n equals 1, n equals 2. So delta x equals n, which we said was 2, lambda, that's 700 times 10 to the negative 9, always have to work in meters, times L, which is 2 meters, all over D, which is 0.1 times 10 to the negative 3 meters. I have this coming to 2.8 centimeters. So you've got to go 2.8 centimeters along to find that, what was it, the third bright band. Delta x equals 2.8 centimeters. Now dark bands are a little bit different. If we'll leave those parameters up. Delta x to the fourth dark band. Well, we know that dark bands occur halfway between each bright band. So if n equals 1 gave us this length here, then n equals a half would give us the length of the first dark band. N equals 1.5 would give us the length of the second bright band. So the second dark band, so n equals a half, first dark band, n equals 1.5, the second dark band, to the fourth dark band, that would be n is equal to 3.5. So delta x is equal to 3.5 times 700 times 10 to the negative 9 times 2 all over 0.1 times 10 to the negative 3. I'm going to calculate that now. I have delta x equals 4.9 centimeters. So that's how you apply that formula there. You'll find the fourth dark band, 4.9 centimeters, from the central line there. Now sometimes in an exam or a SAC, they'll ask this tricky question. If you want the bands to move further apart, what do you do with the wavelength, the length, and the distance between the slits? You say, okay, if you want the bands to move further apart, you want delta x to go up. In order for delta x to go up, you either up the wavelength, up the length between the screen and the slits, or reduce the distance between the slits. Because if you divide by a smaller number, you actually get a bigger term. If you want the slits to move closer together, you want delta x to go down. And if you want delta x to go down, you lower the wavelength, which is another way of saying up the frequency. You reduce the distance between the screen and the slits, and you increase the distance between the slits. So by using this formula, you can pretty much deduce what you want to do in order to change the distance between each of these dark and bright bands. So to summarize, if you want to know if constructive or destructive interference is happening, you can sketch the waves emanating outwards, but a better method is to check the path difference between the two sources. If you find the path difference is a whole number of wavelengths, constructive interference is occurring. It looks like this. You'll get an extra big light wave, and you'll get a bright band. That's what's happening along these lines here. If you find that the path difference is either half a wavelength, that's when n equals 0, a 1.5 wavelengths, that's when n equals 1, or 2.5 wavelength, that's when n equals 2, you'll get waves that look like that sum to 0. You'll get destructive interference or a dark band. And when it comes to do the double slit experiment, which operates on the principles of path difference, you've got three parameters: the wavelength of the light that's arriving at the slits, the length between the slits and the screen, and the distance between the slits. If you change any one of those parameters, the distance to the nth bright band will change.